Hi everyone, welcome back. So we are going to continue with example 3.2. So we were just talking about how the position versus time graph here, this slope is what we use to calculate the velocity. Okay, so what we have here is from 0 to 0.5 seconds, okay? There is an increase in position, right? It goes from 0 to 0.5 meters, okay? And then we have, as time goes on, no movement, so the position stays the same to 1 second, okay? And then from 1 second to 2 seconds, the position changes again, but now from 0.5 meters to 0 meters. Okay, so we're going to use this in order to calculate each of those individual velocities and therefore the slopes to determine the velocity versus time graph. Okay, so I'm going to call this first bit V1, the second bit V2, and the third V3. Okay, so I'm going to say for V1, the change in position is going to be from 0 to 0.5 meters. Okay, so 0.5 minus 0 divided by the amount of time that went by, which is going to be 0.5 seconds. So this is in meters, that's in seconds. And so we get V1 is 1 meter per second. Okay, V2, as you can see, there was no change in position, so 0 meters, but there was a change in time, and that was from 0.5 seconds to 1 second. Okay, so that'll be 1 second minus 1, or 0.5 seconds, or just 0 meters per second. Okay, then we have V3, which goes from 0.5 as the position to 0. Okay, so our initial is 0.5, our final is 0. So 0 minus 0.5, that's in meters over time, which it went from 1 second to 2 seconds. So that'll just be 1. Okay, so this is going to be negative 0.5 meters per second. Okay. Now we want to graph this. So go ahead and draw like that. We have 1, 2, 1, 2. This is going to be negative 0.5, negative 1. This is going to be 0.5, this is going to be 1. So this is the velocity in meters per second. And this is going to be the time in seconds. Okay. We go to 2 seconds. So we're going to have 1, or actually 0.5, 1, 1.5, 2. Okay. So 0.5. Okay. Just 2 seconds. Okay, so our first little bit, V1, is at 1 meter per second. Okay, and that's until we hit 0.5 seconds. Okay, so 1 for 0.5, so I'll end here. So how we draw this is going to be a straight line. Okay, this makes sense because the velocity is staying constant. Okay, we don't have it depending on anything other than time. Okay, so it's going to be 1. Then we have 0 from 0.5 to 1 second. Okay, so we're going to just thicken that line. So that's our second velocity. Now our third velocity is negative 0.5. So here, and that's from 1 second to 2 seconds. Okay, so this is how you draw that graph. There's going to be either a break, you can draw it like that, or you can connect these. I'm not going to be too picky about that if I ever have you draw these, but technically I do believe it would be dotted, okay, since the graph jumps down, okay. So this is another example of graphing, position versus time, and then velocity versus time, okay. All right, so let's go ahead and move on to our next example. This is going to be example 3.3 in your textbook. It states the position of a particle is given by this equation, x of t equals 3t plus 0.5 t cubed, and that would be in meters since it is a position. Okay, it says using these two equations, which those two equations are really just telling you how to take your derivative, okay? Find the instantaneous velocity at t equals 2 seconds. Okay, so for A, we want to find the instantaneous velocity, so we need to take this equation and determine the velocity. Okay, so v of t is equal to d dt of x of t. Okay, so we take the derivative. This is going to be 3 plus, pull that guy down, 3 times 0.5 t. Now it's going to be squared instead. Okay, or 3.0 plus 1.5 t squared. Okay, and we're just going to remember the units on this is going to now be meters per second since it's a velocity. Okay, so the instantaneous velocity at t equals 2 seconds. All we do is plug that in like any normal equation. So 3 plus 1.5 times 2 seconds squared. So we can leave that off for now. Plug that into your calculator, and you get 9 meters per second. Okay, so this is the instantaneous velocity at that time, t equals 2 seconds. Okay. Now for part B, it asks, calculate the average velocity between 1 and 3 seconds. So what you'll do is you'll find your position of both of these, right? So, okay, let me back up a little bit. Your average velocity is equal to the change in position over the change in time. Okay, so we want to know the position of our final placement, which is going to be the 3 seconds, minus our position of our initial, which is 1 second, okay, over our change in time, which is going to be 3 seconds minus 1 second, okay. So what you'll do is you'll plug these values into that first equation here, x of t. Okay, so imagine if I have x at 3 seconds, you'll plug it in here and here. So 3 times 3 is 9 plus 0.5 times 3 cubed. And doing that math, you get 22.5. Okay, and that's meters, minus, do the same thing for 1. Okay, and you'll get 3.5 meters. Okay, and you have 2 seconds on the bottom. So then you get 9.5 meters per second. Okay, so that's what that means by the average velocity between these two times. Okay? All right, so moving on now to acceleration. This is going to be similar to how we found velocity. Okay, this is going to be another rate of change. Okay, so average acceleration is the rate at which velocity changes. Okay, so it's going to be the change in velocity over the change in time. Okay, acceleration in general is a vector. Okay, and it is in the same direction as the change in velocity. Okay, instantaneous acceleration, a of t, is an acceleration at a specific instant in time, just how we defined velocity, instantaneous velocity. Okay, it's going to be the derivative of the velocity. Okay, derivative with respect to t. So you can look over here at these different graphs. Okay, these are all velocity, or these are velocity versus time graphs. Okay, just kind of showing you the difference. Okay, so let's see. We can look at these two down below, the difference or the relationship between velocity and acceleration. Okay, so remember when we were looking at the position versus time graph and the velocity versus time graph, their relationship was that the velocity one, or to calculate the velocity, you found the slope of the position change with time. So it's the exact same thing now. So if we have this graph here, we can calculate it just with this little guy and this little guy. So we have the position, the initial position is 3. Let me see. 3. And our final is 0. So this is going to be change in velocity over change in time. Okay, now our change in time went from 0 to 0.5 seconds. So that change is 0.5 seconds. So this is meters per second. This is in seconds. And I get negative 3 divided by 0.5, which is 6 meters per second squared. So this is a slope, right? We just found the slope of that of this line here, rise over run. Okay, this is the acceleration. Whoops. Okay, so now you can see that our acceleration is negative 6 meters per second squared. Okay. All right, so hopefully that made sense. I'm going to go ahead and move on now with an example. So this, I'm going to basically just describe it, and then we'll have to finish it in our next video. I like to give a lot of examples throughout. That way you guys can kind of follow along, try the examples out on your own. If you want to like pause the video and try it, feel free to do so. That's totally awesome if you do that. You don't have to though. You can just follow me and try to understand what I'm doing, and then you can always repeat it. Maybe that'll help you with the homework and so forth. Okay, so this one is example 3.6. It states a particle is in motion and is accelerating. The functional form of the velocity is v of t equals 20t minus 5t squared, and this is in meters per second. It states, find the functional form of the acceleration. Okay, so what is the functional form? That just means the equation that describes the acceleration. Okay, so I'm going to do that right here. So remember that acceleration is the derivative with respect to time of our velocity. Okay, so a of t is going to be the derivative with respect to t, so it'll be 20 minus 2 times 5t, or 20 minus 10t. And this is now going to be in meters per second squared. Again, don't worry about it too much. Just remember to keep track of your units. Okay? All right, we'll finish this in the next video.